Good evening once again. This is Dr. Belga Berg, faculty member at Department of CSE, AI and ML Cybersecurity, Jane deemed to be University. Welcome to another session of Industry Connect program. Today's guest speaker, Mr. Sudheendra Rao K, is a data scientist, entrepreneur, and a professional trainer. He is the co-founder of Data Law Labs, which offers services in consulting, staff augmentation, project implementation, and corporate training in machine learning, deep learning, R, and Python. Mr. Rao's expertise spans over a multitude of areas like Python, R, data analysis, machine learning, deep learning, computer vision, NLP, predictive modeling, and algorithm development and implementation. Currently, Mr. Rao is a data science consultant at Chrysopia. Today, he will be interacting with you on the topic Supervised Machine Learning Algorithms, Random Forest. We are glad to have you here with us, Mr. Rao. Welcome to Jane deemed to be University, and the virtual podium is yours, sir. You can start now.
Thank you so much, ma'am. Thank you so much for the introduction. Let me just go ahead and share my screen. Okay, so please let me know if you're able to see my screen.
Yes, sir. We can see your screen.
Okay. Yeah, thank you, ma'am. So hi everyone. So ma'am gave a very good introduction about me. So today I'll be talking a little bit about what is a random forest algorithm, what kind of problems can be solved, what is the math behind this, and how do we train a model with random forest. Just a quick demo in the end. Okay. Before we start talking about random forest, I would like to talk a little bit about supervised and unsupervised learning algorithms. Okay, you might have heard of these terms too many times in maybe you have read it in blogs, your notebooks, sorry, your textbooks, or your professors would have told you, right? So what exactly is supervised learning and unsupervised learning, right? So supervised learning is when you train a model where you already know the output. Okay, what I mean by that is, like, for example, if you're building a model for, like, let's say predict temperature in Bangalore, right? So what you do is you provide a lot of historical data where you provide something like, okay, historically these were the measures, or like these were the feature values, and this was the final temperature on that particular day, right? For example, this was the population, this was number of vehicles, this is how much rain we had, this is the wind speed, and then you will have a temperature column, right? So what you do in supervised learning is you collect a lot of these kind of data points, historical data points, and then you train the model with this. Okay, since you're providing the output column also while training the model, these are called as supervised learning algorithm. Okay, basically, yeah, I mean, whenever you have a machine learning algorithm, right, you just use your common sense, try to understand the English meaning of the word, and you will have half of your answer there. Okay, in this case also, like, supervised learning has an English word supervised, right? So what it means is you're just supervising the algorithm by saying, okay, these are the inputs, this is the output, try to see what you can find, right? So what happens in supervised learning algorithm is the models or the algorithm that we use in supervised learning, it tries to see what is that pattern that actually what is that pattern that actually that actually, like, links this input to output, right? So what it will do is it will take these inputs, it will try to see, try to find some kind of a pattern that actually matches the output, and that is how the supervised learning algorithms are built. Okay, in supervised learning, again, mainly we have two types of algorithm, or instead of calling them algorithm, I would call them as problem types. Okay, one of them is called regression, the other one is classification. Okay, so whenever you have a supervised learning problem where you're trying to predict a continuous value output. Okay, for example, temperature can have like infinite number of possible values, right? It can be 1 degree centigrade, it can be 2, it can be 10, 50, 20, whatever number, right? It could be any number between these numbers also, like 20, 21, it could be 20.5 also, right? If you actually think about it, you can come up with like infinite number of possible values for this, right? So those kind of values are called as continuous values. And whenever you have a continuous value that needs to be predicted, you use an algorithm called as regression. Okay, The other type is called classification. It is the other way, like instead of predicting a continuous value output, you will be predicting something like a discrete value output. Okay. For example, if the disease is present or not. Okay, these kind of things like yes or no kind of problems are like mostly solved using classification. Or it could be like more complex also. For example, you would have heard of this self-driving cars, right? So for in self-driving cars, you might have a model that predicts what is the traffic light, right? Is it red, green, or orange, right? So that is again a classification model because you have you have like you have finite number of possible outputs, right? Your output in classification models can't be like infinite numbers. Okay, so it can, for example, as I said, this self-driving, right? It can be red, green, or orange, right? It can't be anything else apart from these three values, right? So this is called as classification model, and regression and classification are the two very important algorithm types or model types or problem types under supervised learning. Okay, and when we come to unsupervised learning, it is the other way. Like in supervised learning, we have the output to be trained on, but in unsupervised learning, we don't know that output. Okay, so what happens in unsupervised learning is we'll not have the target value. As a result, we will not be able to really build a predictive model here, whereas it will be something like a cluster or like a segmentation kind of problems that we are trying to solve in unsupervised. Okay. Again, just like regression and classifications are examples for supervised, in unsupervised learning, you have algorithm types like clustering. You have a huge amount of data and you want to like group them based on similarity of data points. You can go ahead and use clustering. Okay. And another example for unsupervised learning could be like PCA or SVD, like principal component analysis or singular value decomposition, right? So again, when you have a huge amount of data, like when I say huge amount of data, let's say our data set has hundreds of columns. Okay, you can actually bring down the number of columns into a something like that is manageable, and for that you will be using some of the dimensionality reduction problems like PC and SVD. Again, I'm sure you would learn all these, or maybe you have already learned in the course. But yeah, I mean, these are the again examples where we will not be using any target variables. Basically, we'll just have features and we work with them and try to mine some meaningful information out of that. Okay. Again, don't worry about these algorithm examples. You can easily add another 100 examples here, but yeah, there are a lot of algorithms that we can use for solving supervised learning and unsupervised learning. And one such algorithm that is used for supervised learning is called random forest, right? So let's just jump to random forest. Okay. But before talking about random forest, it's very important to know another algorithm called as decision tree. Okay. Again, as I said earlier, if you just try to make sense out of these words, right, you have half the solution there. Okay, so what exactly is decision trees, right? So it has two words, decision and trees, right? So all of you know what is a tree, right? It will have a root, it will have branches, and it will have leaves at the end of it, right? So in decision tree, what happens is we use a data structure, or let's say yeah, you can call it as data structure, which looks like a tree where we have a root, we have branches, and we have leaves, and we somehow come up with this kind of a structure from our data and try to solve our classification or regression problem. Okay, and why is it called decision tree? Because trees already we know, because it comes up with something like this, a tree kind of thing that we can use for solving our classification or regression problems. And why is it called decision trees? Because at each of these branches, we kind of take a decision as to go like in which branch we have to like go. Okay. Again, if you didn't understand this, don't worry. I'll give you an example so that it becomes very clear. Okay. But yeah, I mean, the whole concept of decision tree is like when you have a data set, we build something like a tree that looks like this, that actually solves your classification problem. Okay. But before decision trees, again, there is one more concept that you need to understand. It's called entropy. I'm sure everybody would have heard of this word entropy in your 12th standard physics or chemistry, right? So entropy is something like it's a measure of like randomness in the system or measure of predictability in the system, right? So so if your entropy is high, that means the randomness in the system is high or the predictability of that system is very high. Okay, if your entropy is zero, that means you can easily predict what that system is. Okay, so we will be using a concept called entropy to solve this classification problem. Okay, I'll give you an example of classification in case of decision tree and random forest, but it can be easily extrapolated to regression problems as well. Okay. Um, okay, having said that, what exactly is entropy in this case, right? So whenever we start with a data set, right, for classification, we'll have, let's say, again, we'll take a simple example of binary classification. Okay, we have just two classes. In this example case, let's say we have two classes, play and don't play. Okay, so we start with a data set that will have mix of both play and don't play, right? So now let's say, okay, I said entropy is a measure of predictability, right? So I have a question for you. Like, let's say we we blindfold you and ask you to pick a data point from this entire data set. Okay, can you predict what that data point is? In this case, let's say it is 9 and 5, right? There are 9 examples from play class and 5 examples from don't play class. So if you pick a data point from here, it could be either play or don't play, right? But the probability of play would be 9 divided by 14, because out of 14 data points, you have 9 data points that falls into play class. So if you pick something without really knowing what it is, there is a probability of 9 by 14 that it could be play. Similarly, if you pick another one, there is a probability that it is 5 out of 14 don't play, right? So this is, so if you see this example, right, this system is like non unpredictable, right? Or in this case, it is still okay, like there is a higher chance of getting a play, right? But what if it was 9 and 9, right? If you actually think about 9 and 9, you have equal probability of getting a play or don't play, right? So the entropy of such systems where you have equal number of data points is the highest, which is 1. There is a very simple mathematical equation. Okay, it might look very complicated here, but basically what you're doing is you're trying to see the probability of each class. In this case, you have two classes, so you have to get the probability and multiply that with log 2 of probability and sum it for all the classes. Okay, and if you just make this calculation for this 9 and 9, you will get entropy value as 1. Okay, entropy value of 1 means the system is extremely unpredictable, or predictability of that system is 0. Okay, whereas let's take another example where you have 9 data points from play class, but no data points from don't play class. Now if I do the same exercise, right, blindfold you and take one data point, you can easily say that that will always be play class, because there is no other data point from any other classes, right? So this is one concept that we use to actually classify these data points. Okay, again, it might be slightly complex at this point of time, but I'll give you another simple example here, then that makes it very clear. Okay, so this is how we actually this is the concept that we use to actually solve this problem. Okay, um, again, that is how we use entropy for classifying. But as I said, there is one more piece, that is decision, right? So as I said earlier, at each of these things, okay, before that, sorry, when you have this data set, right, what you're trying to do here is you're trying to split this data into smaller pieces, so that this entropy of the system reduces. Okay, for example, let's say you have this 14 data points here, right? Based on some decision or some rule, if you're able to split this into two pieces, where you have, let's say, 9 play classes here, play data points here, and 5 don't play data points here, you have basically solved the problem, right? um, yeah, let me give you an example here. Okay, before that, some uh, terminology is required to understand these algorithms, because you will be hearing these words everywhere. Whenever we create a decision tree like this, right? So this initial one is called as it's called as root node because that is where everything starts. Your entire data set starts as a root node, and you keep splitting based on certain rules. This is where the algorithm takes a decision and it splits the data into multiple pieces, and those are called decision nodes. Okay, and you keep doing this till you hit leaf nodes. Okay, leaf nodes are nodes which require no further splitting. Okay, uh, again, let me give you a simple example here. Okay, let's say I have a data set that looks like this. Okay, I have a simple data set. I have a feature where I've asked the person if the person smokes or not, and then we have the output, which is a disease. Okay, now what we want to do with this is we want to predict disease based on the person smoking habits. Okay, now if you see this data, right, what happens is this is the root node, right? Let me just bring this here. Yeah, now if you see, this is the root node where we start with all the data points. Okay, now what I'll do is since I have only one feature here, which is smoking, I'll go ahead and use that. Okay, and if you see, smoking is actually a categorical value, right? It has only two kinds of value, yes or no. So all the yes data points will come here, all the no data points will come here. And if you see this, wherever smoking is yes, see that is serial number 1, 5, 6, 8, 9, and 10, right? 1, 5, 6, 8, 9, 10 comes here. And if you see the disease, all 6 out of 6 data points that came here, everybody had a disease. Okay, similarly, the other branch that we get is smoking is no, and the data points that will go here would be 2, 3, 4, 7. And if you see, those are all the examples where this is no. And if you actually see this tree, right, we have already solved this problem. Okay, what we do is we take the data set, we check for smoking. If the person smokes, we predict that the person will get disease. Okay, if the person doesn't smoke, we can predict that the disease is no. Okay, so this is as simple as that. Okay, so this is a very simple ideal example that I've given here, I've taken here. But not all the problems will be as simple as this in your real-time scenarios or corporate projects. Okay, you might have you might not be able to get this kind of splits easily. Okay, so in such cases, what happens? Yeah, now if you see, again, I've okay, let just see here, I've just changed some of the data points output here. Okay, so now what happens, again the same data set for smoking. Okay, if you split based on smoking, we get 1, 5, 6, 8, 9, 10. 1 is yes, yes. 5 is again yes. 6 is also this is yes. 8, 9, 10, yes, no, yes. So now if you see, all not all 6 of them are disease, right? So there is one data point which is like the person smokes, but he doesn't have a disease. So in such cases, what happens? Will again, this will be the model, but in this case, what happens? Whenever we build a model and we get the input value as smoking as yes, we predict that the disease is yes with 100% probability. Okay, or we are 100% sure that that person will get disease. Okay, whereas in this case, what happens, since we have mix of both the classes here, we see which class has highest number of data points here. In this case, it is disease, which is 5 out of 6, and one of them is no disease. So whenever we get input value of smoking, we predict that it is disease, but not with 100% probability score, but with the like 5 by 6 probability score. Okay, similarly here also, like I have just changed the output for 2 of these rows so that we get like unclean branches or heterogeneous branches. Okay, but this is how it works. Sometimes what happens, you might not have a very simple data set like this, right? I mean, in this case, you don't even need a machine learning model. You can simply put some if else conditions and should be able to solve. Okay, but the whole problem becomes very difficult when you have like more than one columns, right? So let me just take the same example here. Now I have one more feature here, okay, which is called drinking. Okay, now I have smoking and drinking, and then I have the output as disease. Okay, This is the exact same data that I used in the previous slide. I have just sorted it based on smoking, and I have got this drinking column as one more additional feature. Now what happens, you get this, right? Now what you can do is you can further split this data into disease or no disease based on the remaining columns. In this case we have drinking, right? So we can actually further split it by drinking. If you see 1, 5, 6, 8, 9, 10, right? 1, 5, 6, 8, 9, 10 are smoking equal to yes, and out of these 6 data point, 5 are yeses and 1 is no. So we have these data points. Now if you further split it based on drinking, you'll see that wherever it is yes, we get the disease as yes, and wherever it is no, we get disease as no, right? So now this is how a decision tree rule is built. Okay, so now what happens, whenever a new data point comes in and we want to predict, we check what is smoking value. Okay, if it is yes, it goes in this direction. Okay, we come here. Now we check the next condition, which is drinking. If the person actually drinks, we come here, and this is like disease, right? So we say that, okay, the person, we predict that disease is equal to yes. Okay, whereas if it comes here, we predict that this is equal to no. Okay, so similarly, if the smoking is equal to no, we come here again. If you see this also, right? I mean, we don't have a clean branch yet. What I mean is, this system is not, entropy is not equal to 0 for this branch. Only for this and this it is 0, because we have all similar data points here, right? 1, 5, 6, 8, 10. If you see, everything falls into yes class. Okay, similarly 9, since it's only one data point, it will be a entropy equal to 0 branch. But yeah, I mean, in decision tree, what we do is we start from here with some entropy, we keep splitting it based on that mathematical formula I showed, and we keep doing this until we hit these branches which are clean. Okay, our entropy of that system is 0. Okay, uh, sorry. Now if you remember that terminology slide I shared, so this is called as leaf, this is called as root node, because this is where everything starts. Okay, and this is the decision that we take in the first split, and this is your decision node, because it can be further split because it is still not clean, and we do that using another feature, again another decision. And finally we have this branch which is clean. When I say clean, all the data points in this branch falls into one single class. Okay, in this case all the entropy calculations are done on this target class. Okay, so if you see this, everything falls into yes class. So this is a clean branch, or a branch with entropy equal to 0, and this also is anyway one data point, so entropy will be equal to 0. Okay, now let me just quickly go back to this first slide. Okay, so this is what will be used to calculate what feature to be used first. Okay, again, like in this case, I used smoking first and then drinking, right? But what happens if I use drinking first and then smoking as the second feature, right? So this will be solved by using something called as information gain. Okay, what is information gain? We start with the data set, right? Let's say we have 100 data points. Okay, what we do is, let's say our data set has 100 data points and 10 different features. Okay, what we do is we try to split based on each of them, each of those 10 features. Okay, and we see that resulting branches, right, whatever we get here, what is the entropy of this resulting branch? Again, that can be calculated using another formula that looks like this. Again, it might look complicated, but it is very simple. You just have to calculate probability of each branch multiplied by the entropy of this system, like 2, 3. Again, put it in this formula and you should be able to solve it. Okay, now once you calculate this entropy of this entire system, you start with certain entropy and you'll end up with certain entropy here, right? So whenever you split based on some feature, your entropy will always decrease or maybe remain same. Okay, it can't increase. You can't start with the entropy of 0.5 and when you split it, entropy becomes 0.6. That is not possible. Entropy always decreases when you split the data. So if, let's say, a hypothetical example, we start with entropy of 1 and we split based on the first feature, and the resulting entropy of the entire branch is, let's say, 0.8. Okay, then information gain is nothing but what is that decrease in the entropy. Okay, in this case 1 minus 0.8 is 0.2, right? So 0.2 is the information gain for the first feature. Okay, so when we have more than one features, what we do is we calculate this information gain for all the features. Okay, let's say we have 10 features, we calculate information gain for each of those features, and then we take that particular feature that has the highest information gain and we split the data using that decision here. Okay, and when we get these branches, right, we check if they're clean or if they're pure. If they're pure, we don't have to do anything because entropy is 0. We can't further split it because we have already solved that problem. But whenever we have mix of the classes or entropy is not equal to 0, that is again a new problem, because here also we started with the same thing, right? There is certain entropy, we are trying to reduce it to 0, right? So this is again a new problem. Only thing is we can't use this feature again anymore here. It has to be a new feature. Okay, that is only true when the features are categorical. If it is numeric values, we should be able to use it again. Okay, but the whole concept of decision tree is this. Okay, you start with certain entropy, you find out the feature that has the highest information gain, you use that feature here, split the data into smaller chunks, and see if they are pure or if they're homogeneous in the sense all the data points of this branch will be of the same class. If not, then further split it using the remaining features. Okay, you keep doing this again and again and again till you hit pure nodes or nodes with entropy equal to 0. Okay, and these final nodes that you get which are pure, right, those are called as leaf nodes. Whichever are impure, these are called decision nodes, and whatever we start with the beginning, that is called as root node. Okay, so that is how a decision tree is built. Okay, uh, but actually okay, um, in this case these are categorical values, but if you just use a numerical value here, you should be able to visualize it like this as a xy coordinate graph. Like let's say this is x value of the data point, and this is the y value of the data point. Let's say if we have something like this, instead of splitting like this, we have to split like this, so that entropy is 0 in this case. Because if you see this split, right, this is one region, this is the other region, and both the regions are like homogeneous, right? So this is a good split, and this is a bad split. Okay, what exactly the split means here? As I said, this is x value, this is y value, right? Or this is x value, this is y value. In this case, if you split the data based on x feature, you don't really get a good separation. Instead, if you split it based on y feature, you get a good split. Okay, this line is nothing but you're saying, okay, these points are all y value greater than let's say if this is 5. Okay, y value greater than 5 is this region, y value less than 5 will be here, right? But if you split it based on x value greater than 5, x value less than 5, it doesn't really make sense here, right? I mean, this is not actually trying to solve the problem. Whereas here we will be able to separate blue classes from yellow classes, right? So this is how decision tree works. Again, these are all ideal scenarios that I'm talking about. In actual scenarios, you'll have a huge data set with like hundreds of features. You have to see like what are those features that has the highest information gain, and then from there onwards you have to go and like split the data. Okay. Okay, just to put the steps into words or like pseudo algorithm code. What we do in decision tree is we start with the target variable. We calculate the entropy of the target. Okay, if it is like multi-class, you can also use this entropy calculation to sorry, you can use that formula that I showed earlier to calculate entropy of the system. But if you have a binary class also, you should be able to use the same formula. Okay, so what we do is we start with entropy. We calculate the entropy of the system or entropy of the data set. Then what we do is we split the data with each of the features that we have in our data set, and we try to see like what is the entropy gain or information gain that we get from each feature. And we use that information gain to see like which feature has the highest information, and we use that to split. Okay, and then the resulting branches that we get is further split till you get branches with the entropy as 0. Okay, so this is how a decision tree works. Okay, uh, although it's a very simple algorithm, there are like a lot of negatives about decision trees. There are some positives also, but decision trees are like not widely used in classification models because they have some negatives about it. Okay, but before negatives, we'll talk a little bit about what are the positives of these decision trees. So the first important pro of the algorithm is it does feature selection, right? So if you see this data set, or in our data set, right, we have this data set. If somebody asks what is that feature that has the highest importance in finding out if the person will get disease or not, right? You see that smoking has the highest information gain. So you can say that, okay, smoking is the most important feature here, followed by drinking, and maybe like if you have more features, you should be able to calculate that. Okay, but based on that information gain, you should be able to say which feature has the highest information gain, and or which feature is the most important feature in trying to solve this problem. And that is one of the biggest advantage of this algorithm, because a lot of algorithms are actually black box algorithm. You won't be able to understand what is happening inside, whereas this decision tree is a very simple algorithm. It will tell you like what is that feature that is actually impacting a lot in predicting the target variable here. Okay, and it can also discover nonlinear relationships. Okay, if you go back to this problem, right, it is again a very ideal scenario where we have like all the data points can be separated by just one line. But in actual scenarios, the data will be much more complex than this. You need to have like very complex decision boundaries like this. Okay, and decision trees are very good at giving you that kind of non-linear decision boundaries. Okay, and these are not affected by outliers. If you actually think about the disease prediction that we did, right? If you remember, there was one data point which was smoking equal to yes, but drinking was no, and we were predicting it as no, right? Actually, if you think about it, that is an outlier. Outliers are like data points which are not following the regular trend. And if you have an outlier in decision trees, outlier data points, your decision tree structure will not change like too much. Maybe a small branch will get added in your decision tree. Okay, apart from that, nothing happens. That's why this is not affected by outliers. Okay. And the most important thing here is it is easy to interpret. Okay, so as I said here, right, I mean, it's very easy to give you the or it's very easy to understand the model that we have come up with, and we should be able to share it with anyone, right? If somebody asks what is the model, okay, how does it predict disease, okay, we can easily say, okay, what we do is we first check if the person smokes. If the person smokes, historically we have found that out of 6 data points, five of them had disease, so we predict that that person has disease. But what we can do is we can further check if the person drinks. If the person drinks, then we are very sure that he has a disease. But if he doesn't drink, maybe we think that it's a no disease, right? If you see this tree, right, it's very easy to parse and very easy to understand for anyone, right? So that is one of the very important pros of decision tree. Okay, as I said, that was the last point. Actually, generated rules, we can easily share it with anyone. We can explain it to even a layman. Okay, whereas other algorithms, it's not this easy. It will come up with extremely complex mathematical equations which will not be able to understand. Okay, so that is one of the biggest advantage of using decision trees. Okay, but as I said, there are some cons also. One of the biggest cons of decision tree, or like negatives of decision tree, is this overfits. Okay, I'm sure you would have learned about overfitting and underfitting, right? Overfitting is simply like how well the model performs on unseen data set. Okay, so overfitting is when you have your training data and test data. On training data, it performs really well, but on test data, it performs very poorly. Okay, because what would have happened in the model is it didn't learn the exact pattern. Instead, it tries to like by heart the data set itself. Okay, as a result, what happens? It overfits, so it doesn't really generalize for your data set. Okay. So this is how decision trees are built. And another thing is decision trees do not work really well if you have smooth boundaries. For example, in this case, if you see, it's a very clear boundary, right? But let's say there are some stars here in between, and there are some blues here, right? It has to come up with extremely complex decision boundary like this. Like it has to separate these blue points from yellow points, right? So it tries to come up with extremely complex decision boundaries, and as a result, it overfits. Okay, so that is what I mean by they don't really do a really good job when we have smooth boundaries. Okay, and another thing is super attributes will give higher information gain. Okay, sometimes we might have some features or columns that will have too many values. Okay, for example. Let me just give an example. The same data set. Okay, let's say there is another column called country. Okay, and let's assume each of these people are from different countries. Okay, now if you actually use that country column here, what happens? Each of these data point will be split into a separate branch, right? India will be one branch. Let's say Sri Lanka will be another branch. US will be another branch, and so on, right? So if you see, each of those branches are like pure branches, right? Because you have one person in the first branch, you have only yes. Second branch, you have only yes. Third branch, you have only yes, and so on, right? So as a result, what happens? It identifies that feature as the most important feature because the information gain for that feature will be like highest, right? So what happens is, but if you actually think about it, did we solve the problem? No, right? I mean that country is like a super attribute. It has too many unique values, and that is the reason we got this kind of a split. Okay. Uh, but yeah, I mean there are some implementations of decision trees where we actually like normalize that information gain with a number of branches it creates. Okay, if it creates too many branches, the information gain will be like reduced. Okay, but this is how decision trees are built. Okay, now before jumping into sorry, before jumping into random forest, right? We have to talk about something called as bias variance trade-off. Okay, what exactly is bias variance trade-off? Okay, so in case of the decision tree models, right? Decision tree models are like very complex models. Sorry, decision tree models are very complex models, and they have very high variance error. Okay, before that, let me just talk about what is bias error. And just give me one second. Yeah, so before talking about before talking about the random forest, we'll talk about bias variance trade-off. So there are two types of error whenever you build a machine learning model. Okay, one of them is called bias error. So if your model is very simple, right, it always gives you the same output. As a result, what happens? Your model will do poorly on both training as well as testing. Okay, and if your model is extremely complex, then what happens? Your model will perform really well on the training data set, but on test data set it performs really poorly. Okay, so we just draw this bias and variance errors on with respect to model complexity, right? This is how it looks like. So if your model is too simple, your bias error will be really high, and variance error will be low. But if your model is extremely complex, your variance error will be really high, and bias error will be very low. So whenever you build a model, you have to hit this sweet spot where you're like balancing both of them. Okay. Otherwise, what happens? Your error will be like either bias model, or it will be like a higher variance model. Okay, which is not good for like predicting. I mean, you will not get meaningful predictions out of these models. Okay, that's why you have to hit this sweet spot where you set the model complexity to a certain level so that bias variance errors are like traded off. Okay. And how do we do this for decision trees? One of the things that we can do is we can actually like do something called as tree pruning, where we actually cut the tree at a certain height so that further predictions are not done. But even better than that is something called as a bagging algorithm. Okay, so what exactly is bagging? Bagging is an ensemble model. I'm sure everybody would have heard of the word ensemble, right? It just means multiple things working together, right? For example, Avengers, right? Avengers is a ensemble of superheroes, right? Because instead of one person doing the job, multiple people come together and do the job for you. Okay, so that is called as ensemble models, and bagging is one such algorithm. Okay, or algorithm type. Okay. So what happens in bagging is you have your data set, right? What you do is you create multiple data sets out of that. Okay, like it could be like, let's say we have 1,000 data points here. You take a random subset of 500 data points. Okay, then what happens whenever you have like multiple data sets like this, all these data sets will be different from each other, right? Then what we do is, okay, before this, let's say you have a data set, you try to build a decision tree, and even if you build it 10 times, right, you will always end up with the exact same decision tree, right? Because all the steps that we calculate, that entropy calculation, information gain calculation, everything that we do, nothing changes even if you send them data multiple times, because there is no randomness in the system here, right? Everything happens based on these rules, right? So what happens? The whole concept of bagging is, as I said, ensemble, right? Instead of one model doing the job, we want multiple models to do the job for us. Okay. For that, what we need is, first thing is we need multiple data sets, and then we need multiple models out of that, and then we try to combine them together and say, okay, this is the output. Okay. But as I said, if you use the same data set to build decision trees, it will always give you the same exact same output, right? So there is no point in using the same data set multiple times. Okay. So what we do is we have to bring some randomness here, right? So what we do is, instead of using the entire data set again and again, we try to do something called as bootstrap aggregation. Okay. Or random sampling. Okay. So we have 1,000 data points here. We randomly select, let's say, 500 data points here, 500 data points here, 500 data points here, and so on. Okay. And since we are doing random sampling, all these data sets will be different from each other. Then what we can do is, for each of these data sets, we can fit a decision tree model. Okay. And then what we can do is we can combine all of them using some kind of a bagger. Bagger is nothing but like, it could be as simple as like taking average, or like trying to see, it's like voting. Okay. Let's say the first model says output as class 1, second model says class 2, third model say class 1, right? Model 1 and model 3 are saying class 1, model 2 is saying class 2, and we predict it as class 1 because 2 out of 3 has said class 1, right? So that is what bagger does. Okay. Okay. So why I'm talking about bagging is because we have an algorithm called random forest, which is nothing but decision trees plus bagging. Okay. So what happens in random, again, it has two English words, right? Forest, because uh, forest is nothing but multiple trees together, right? So in this case, random forest is an algorithm where we build like multiple decision trees, maybe like hundreds of decision trees together, and try to make prediction out of that, or combine all of them together, like ensemble of these trees. Okay. And it also has a term called random, because we introduce some randomness in the system so that this data set is different, or the models are different from each other. Okay. So we actually introduce this randomness in two steps. One, as I said, when we create these data sets, right, we do we use random replacement with random sampling with replacement. Okay. So that the data sets are completely different from each other, and only when they're different, it makes sense to build a model. Otherwise, it will always result in the same model. And the second thing is, if you remember decision trees, right? At each split, what we do is we take all the features and we see like which of those features has the highest information gain, right? In random forest, what we do is we don't take all the features, we take a random subset of it. Let's say if you have 10 features, we don't really consider all the 10 features at each split. We'll take a random subset of a much smaller number, let's say three features. Okay, we have, let's say, feature 1 to feature 10. In case of decision tree, we can, let's say we find that F7, feature 7 is the highest information gain feature. But in random forest, what we do is we don't do that. We randomly select three, let's say 1, 4, and 6. Okay, out of these 1, 4, and 6, we try to find out which of these features has the highest information gain, and we split the data. Okay, and and in each split, that random selection of features changes, and as a result, what happens is we get multiple multiple decision trees from the same data set. And finally, what we do is we use this data set to predict, like what happens whenever new data point comes in. It gets predicted from this model, this model, this model, all the models. And finally, as I said, we do the voting of these. Like let's say in this case we have 6 models. 5 of them predicts that it is, let's say, disease. One of them says no disease. We still predict it as disease with probability score of 5 by 6. Okay, so that is how random forest algorithm works. Okay, again, one more thing is random forest, we build like hundreds of decision trees. It depends on your data set. Okay, if you have huge number of data points, like thousands of data points, then it makes sense to build thousands of decision trees. But let's say you have only 100 data points, it doesn't make sense to build 1,000 decision trees. Okay, so the number of trees that you build in random forest depends on the data set size that you have. Okay, and random forest is one such algorithm which can be used to build classification models as well as regression models. In case of classification, it will check that entropy value, right? In case of regression, what it does is it tries to minimize standard deviation in the data set. Okay, uh, again, if you understood the random forest decision tree model, you should be able to easily extrapolate it to regression with standard deviation. Okay, but that is how random forest works. And finally, yeah, this is how it works. Okay, you have a new instance. We have multiple trees that we have built in the random forest, and it will predict. Let's say first model predicts it as 1, 2, 1, 1. We predict it as 1 with probability score of 75%, because out of 4, 3 predicted it as 1. Okay, and when we have hundreds of decision trees, the prediction score will be like minute, like 950 out of 1,000 is predicting it as positive. We predict it as positive with the probability score of 0.95. Okay, so this is how random forest random forest algorithm is built, and this is how it is. This is how it works. Okay, and random forest algorithm is one of the most popular algorithm right now for classification or regression, because because of this ensemble concept. It is very powerful. It can like give you much better accuracy in terms of your predictability in case of classification, or much better R square in case of regression. Okay, so yeah, so this is the theory behind this. So any questions on this? How does it work? Like, do we take questions now or towards the end?
I think we can go towards the end, Sudheendra.
Okay, okay, cool. So let me just quickly show you how to build. Sorry. Yeah, let me just open collab. Let me just show you a simple example of random forest implementation. Okay, yeah, let me just open this. Okay, so let me open one Excel file here. Okay, I have a data set which is very popular. You should be able to download it from internet. It's called PIMA in Indian diabetes data set. Okay, so it has certain features like the number of pregnancies the person had, the glucose level, blood pressure, the skin thickness, insulin, a lot of these things. And based on that, we want to predict if the person has diabetes or not. Okay. Now, I would like to use this data set and build a random forest model. Okay, so let me just quickly show how that is done. Okay, what I've done here is I've already written the code and kept it ready so that we don't waste time in like typing the code. The first step is loading the libraries. Okay, so I'm sure you will learn, or maybe you already learned. But NumPy, Pandas, and Matplotlib, these three libraries are like most popular, most used libraries for solving any machine learning problem. Along with this, we also have another library called scikit-learn, which we'll be using to build the model. Okay, so in the first step, I'm just loading all the libraries. Then what I do is I just load the data set into a pandas data frame. Okay, since I'm using Colab, right, Google Colab, which is a free tool, I can just take the file from here and just drag and drop it here, or I can also upload it from here, and the data will be available here. Okay, but only thing is, whenever you close this close the Colab session, your file will get recycled. Okay, so it works if your data set is small, but when your data set is large, you might have to connect your Colab to Google Drive and work on it. But yeah, if your data set is small, this is like you can just directly upload it here and should be able to do everything. Okay. Okay, so in this case, I'm just loading the input file and trying to explore. Okay, let me just quickly run each of these. Okay. So yeah, okay, let me just run this. So in this step, what I'm doing is I'm just loading the data set, okay, as a data frame, and just checking how many rows and how many columns. In this case, if you see 768 rows and 9 columns are there, and I'm using df.columns to check what are those columns. And if you see, these are all the columns in my data set. I just showed you in the Excel. So I want to predict outcome, which is if the person has diabetes or not, based on all these other columns as features. Okay, I can also do, this is a very simple ideal example, okay, which we can show it in like half an hour or 15 minutes. But actually, when we work on a corporate project, this will take a lot of time to create this kind of data set. Okay, we have to scrape the data from multiple places. We have to do a lot of data validation, data manipulation, feature engineering, where we try to add new features based on the existing features. And that itself will take a lot of time. Okay, each, let's say, to build a classification model will take a few months easily. Okay. But unfortunately, this is like 1 hour session, right? So I have to take some like pre-created data set, and I should be able to show you this. Okay. But yeah, I mean, in this case, if you see, it's a very clean data. There is no missing values, nothing. But in actual data sets, we'll have a lot of missing values. You'll have some error data points. So you have to do all those things, outliers, all those things needs to be removed. Okay. But here it is a clean data set with no outliers. So I'm just going ahead and using it. Okay. Once you have loaded your data set and done all the exploration, right, you can go ahead and create your feature matrix and target vector. Again, just to note here, it's called feature matrix because it is always a two-dimensional data structure, features, whereas target is called vector because it's always one-dimensional. Sorry. Okay. That is what I'm doing here. I'm just taking the data set and splitting the first few columns as features and the last column as target. Okay. And now when I print the shape, the first one, it says rows and columns, but this, for the second one, it just says some number and nothing here because as I said, target vector is one dimensional. So it doesn't have one column here. Okay. So that is why it just 768 values. Okay. Once we have done that, we can use the scikit-learn functions to actually split the data into train and test. Okay, because whenever we build models, right, we split the data into train and test. We keep a small piece aside as test set, to validate our models. Okay, otherwise what happens, we have to wait till actual data comes in, then only we can validate. So instead of doing all those things, we can just keep a small piece aside to actually validate our model. Okay, and this should be done randomly. You can't say, okay, I want to keep these data points in test. Don't ever do that. I mean, it will simply add bias to your model. So whenever you split your data set, always make sure you're splitting it randomly, and you have to run it multiple times with multiple training test splits, so that you are very confident that the model that you have built is good. Okay, and yeah, these two lines here, they do that. Now if you see, after splitting, I have 614 rows in training data, feature matrix train, 614 values in TV train, target vector train, and the remaining 154 data point is in test and TV test. Yeah, so the 768 rows got split into 80-20, which is 80% is 614, which is in training, and the remaining 20% is in test. Okay, so this is how we can actually say what percentage of data to be kept as a test set. Okay, and once that is done, you can go ahead and build the model. So it's very simple to build a model using scikit-learn or sklearn library. So what you have to do is you have to just import the model implementation from sklearn like this. In this case, I'm building a decision tree classifier, so that is why I'm just importing that. Okay, let me just remove this. And then what you can do is you can build your decision tree classifier. If you, okay, when you instantiate it like this, right? So it will take all the default values for everything. Like criteria will be Gini index, and you can change it to entropy. Entropy and Gini are two ways in which you can find the purity. Okay, and you can also specify few other parameters like max depth. Okay, by default, what happens in a decision tree, it will grow all the way up to the bottom. Like it tries to get to a leaf node which is like pure. But let's say you don't want to do that. You want to stop after 3 splits. Okay, like you start with root, 1 split, 2 split, 3 split, and after that you don't want any further splits. You can set up, you can specify that value here. Okay, if you just retain like max depth equal to 9, it will go all the way to till it finds that like pure node. Okay, similarly you can also specify other parameters like mean sample split. Okay, what it means is right now it means 2, it is set as 2 by default. So what it means is if the values, or if the number of data points in split is 2 or less than 2, sorry, 2 or more than 2, it gets further split. Okay, so if I set it as 10 and we get a impure node with 8 data points, right? Since this is 10, the number of data points in that impure node is 8. It won't get further split because this is 10, right? This is more than that 8, so it won't further get split. Okay, so similarly you can actually specify all these different features to see like how the tree can be like pruned, or how you can actually avoid overfitting in decision trees. Okay, but initially you just leave it as it is and fit the model. Yeah, and you can also visualize your tree. Right now I'll not do it because it takes some time to plot this tree, but yeah, this tree was plotted with max depth as 4. That's why you see 1 split, 2 split, 3 split, and 4 split. And even if the nodes are impure, if you see this, it has 175 no class and 14 yes class, and even then it won't get further split. Even this one, like there are 3 samples, but still it won't further split, even though it is like impure node. And it is true for everything. Okay, whereas if I just run it like this, it grows the tree all the way till the bottom, and it builds a very complex decision tree. Okay, or if I just change let's say max depth to 2, you will see how it changes. Okay, it might take some time because the figure size is really big. Anyway, yeah, so if you see only 2 splits, 1 split and 2 splits, and this is how it looks like. Okay, if your splits are like if your max depth is very small, the model will be very simple and it might underfit. But if it is too large, the model will be extremely complex and it might overfit. So you have to find a very appropriate value for your data set. Okay, there is nothing like right or wrong values here. For some data sets, max depth of 4 might do a really good job, but for some other data set, max depth of 10 might do a good job. Okay, so that is called as hyperparameter, and it changes for each of your data sets. Okay, you have to find that optimum value of that hyperparameter for the data set that you're training your model on. Okay, anyway, yes. Finally, some model performances like accuracy score, confusion matrix, and all. Again, it is very simple. Like from sklearn, you can import it and you should be able to print it out here. Okay. Again, confusion matrix. And just like how you have built this, right? Decision tree classifier, you should be able to build a random forest model also. You just have to import random forest classifier from sklearn ensemble. And this is where you actually pass how many trees you want to build. Okay, in this case, by default, it is 100. So if it is 100, you don't have to put it here. Like by default, anyway, it will take 100. If you want to build 500 trees, you can do something like this. Okay, and model.fit, and you pass your training and test data, and then you check what is the accuracy of your model. Okay, so for training it is 1, for testing it is 75.75, 75% accurate. Again, you see that this is an overfitting model. Okay, but again, you can also check confusion matrix like this. Okay, anyway, just quickly, once you build the model in random forest, you will be able to access this property called estimators that will have all your decision trees. In this case, we have built 500 decision trees, right? So if you see, these are all the decision trees the model has, and you should be able to access any of these decision trees and like see like how exactly it looks like. Okay, so in this case, I've just plotted 3 decision trees from our model. We'll see how it looks like. Yeah, so this is the first tree that we have in our random forest. The data set is same, but if you see this and this, they are different decision trees, right? So because the data set is different, and in each of these splits, the feature that was selected to split is different. Okay, and this is another one, the last one that I'm printing. And here also, if you see, the decision tree is totally different from these two, right? So this is how random forests are like really good. They actually combine multiple trees together, and it uses that ensembling technique to like take advantage of this individual decision trees, and gives a really robust output as the output for you. Okay. Yes, that's all I had. I can actually share this notebook with like you guys, and even the data set. You should be able to like test it and maybe play with this. Okay, but anyway, this is how simple the implementation in Python for all your algorithms using scikit-learn. Okay. Yes, that's all I had for this session. Anyway, we are 8 minutes like above schedule. So yeah, any questions? Yeah, any questions?
Okay, so if we don't have questions, shall we wind up? So, like, do you want to wait for some more time for the questions?
No, I think it's fine, ma'am.
Okay. So, audience, please fill up the survey form. The link has been posted in the chat box. So, it's time to wind up this session. I thank Department of Computer Science, Engineering, AI/ML, and Cybersecurity, and Future and Technologies for the efforts they take to organize these Industry Connect sessions for our students. We are grateful to our guest of honor, Mr. Sudheendra Rao, for interacting with our students. I thank Dr. V. Vivek, the head of the Department of Computer Science Engineering and Artificial Intelligence and Machine Learning and Cybersecurity, for eminently spearheading the departmental activities. I also thank our team of faculty members for guiding our students in academic and co-curricular activities. Dear students, thanks for participating. We will meet you again next Saturday with another session of Industry Connect. Good night, everyone.
Yeah, thanks everyone. Thanks for the great opportunity.
Thank you again, sir.
Thank you, Sudheendra. Thank you.
Thank you, sir. Yeah, bye. Good night.